This presentation is on the chemistry of the elements in Group 2 of the periodic table. So the arrow here is pointing to Group 2 of the periodic table shown, and it consists of the elements beryllium, magnesium, calcium, strontium, barium and radium. These elements are all metals as they're on the left hand side of the periodic table, and atoms of each of these elements have 2 electrons in their outer shell. Now the first thing we need to look at is the reactions of these Group 2 elements with water, and this is a reaction that you will likely do with your teacher in class. Now when you do this experiment with your teacher, you will be expected to record the observations from this experiment. The first observation you should make is that you should see effervescence, and that means that a gas is given off during the experiment. If you were to collect the gas that's given off during this experiment, it would ignite with a squeaky pop. And you should know from secondary school that the squeaky pop test is the test for hydrogen. If you were to add universal indicator to this experiment, you would see that it should turn purple as the Group 2 metal reacts with water. This observation we will discuss later in this presentation. An important thing to note from this experiment is the trend in reactivity of the Group 2 elements, and you should see that the reactivity increases as you go down Group 2, which means that magnesium is less reactive than calcium, calcium is less reactive than strontium, and strontium is less reactive than barium. We need to construct equations for the reactions of these Group 2 elements with water. For us to be able to do this, we need to know that the products of the reaction are hydrogen, that we found out from the squeaky pop test earlier, and an alkaline substance as the universal indicator turns purple during the experiment. This alkaline substance is actually the Group 2 metal hydroxide. In the general form of the equation for the reaction of the Group 2 metals with water, we can represent any Group 2 metal with the symbol M in this case. Now, as all of the Group 2 elements are solids at room temperature and pressure, we can give it the state symbol S. Now, it's reacting with water, which is H2O, and it's a liquid at room temperature and pressure, so we give it the state symbol L. Now, it produces a metal hydroxide, and since the charge on a Group 2 metal ion is 2+, and the charge on a hydroxide ion is 1-, we need 2 hydroxide ions to balance the charge on the Group 2 2+ ion. So the formula of any Group 2 metal hydroxide is M, open brackets OH, close brackets 2. It is a solution, so we give it the state symbol AQ. And because the reaction also produces hydrogen gas, we give it the state symbol G. Now, to balance the equation, we need to include 2 moles of H2O in this reaction. So here's the equation written specifically for magnesium. You can see that we've just replaced the general symbol for the Group 2 metal M with the specific symbol Mg, but the rest of the equation stays exactly the same. At this point, you can pause the video and attempt the simple equations for the other Group 2 elements reacting with water. Now, we mentioned on a previous slide that the trend in the reactivity of the Group 2 elements is that they become more reactive as you go down the periodic table. Now, we will discuss why this is the case in a little bit more detail in this slide. So we can see that we have the electron configurations for a magnesium atom and a barium atom. And we know from the trend discussed earlier that barium is more reactive than magnesium. If we look at the electron configurations for the 2 atoms, we can see that barium's outer shell electrons are further away from the nucleus than magnesium's outer shell electrons. This means that because the attraction between the nucleus and the outer electrons in barium is weaker than the attraction between the nucleus and outer electrons in magnesium, the outer shell electrons of barium are easier to lose, and that is what makes barium more reactive than magnesium. The next thing we need to discuss is the acid-base character of group 2 oxides and hydroxides. Now here is the pH scale, something I hope you're very familiar with from Key Stage 3 science, and you can see that acidic substances have a pH smaller than 7 and alkaline substances have a pH greater than 7. And you can see that acidic substances turn universal indicator red and alkaline substances turn universal indicator blue. Now, from the experiment that you should have carried out, you should see that the universal indicator actually turns blue. This therefore means that all of the group 2 oxides and hydroxides are basic. What this means is that all solutions of group 2 oxides and hydroxides will have a pH greater than 7, which is why they turn universal indicator blue. Another thing to note is that group 2 oxides and hydroxides will also react with acids, and this is something that we will cover in more detail later on in the course. We do, however, need to be able to construct symbol equations for the reactions of the group 2 oxides and hydroxides with acids. And we will look at the general equation for the reactions of the group 2 hydroxides with acids first. So if we take the example of magnesium hydroxide, which has the formula Mg, open brackets, OH, close brackets 2, this is an aqueous solution in this case, and we're going to react it with HCl, which is hydrochloric acid. Again, this is an aqueous solution, so it is also given the state symbol AQ. Now, when these two react together, we form MgCl2, which is a salt. And because this is also in solution, we again give it the state symbol AQ. We are also producing water as a result of this reaction, which has the state symbol L. In order to balance this equation, we need to react 1 mole of magnesium hydroxide with 2 moles of HCl, and we produce 1 mole of MgCl2 and 2 moles of water. Now at this point, you can pause the video and practice the simple equations for the other group 2 hydroxides with acid. We can also practice the equation for the reaction of group 2 oxides with acids. Now in this example, we have calcium oxide as our reactant, and this has the formula CaO because the charge on the calcium ion is 2+, and the charge on the oxide ion is 2-. So we need one of each of them to balance the charges, and that gives the formula CaO. Now this time the state symbol for calcium oxide is solid because it's not actually soluble in water, so we react it in solid form with the acid. This time we've chosen the acid sulfuric acid, which is H2SO4, and like all other acids we give it the state symbol AQ because it is an aqueous solution. Now the products of this reaction are calcium sulfate, CaSO4, and water. Now the formula for calcium sulfate is CaSO4 because the charge on the calcium ion is 2+, and the charge on the sulfate ion is 2-. So again we need one of each of the ions to balance the charges. The calcium sulfate is also given the state symbol AQ because it is in solution, and the water, H2O, is given the state symbol liquid. If you like, you can pause the video again at this point and practice the equations for the other group 2 oxides with any acid of your choice. The next thing that we need to discuss is the trend in solubilities of the group 2 hydroxides and carbonates. Now unfortunately this isn't something that can be predicted using the periodic table. These are trends that we just need to learn for the exam. The trend for group 2 hydroxides is that they become more soluble as you descend the group. This means that magnesium hydroxide is less soluble than barium hydroxide. The trend in group 2 carbonates is that they become less soluble as you descend the group. This therefore means that calcium carbonate, for example, is actually more soluble than barium carbonate. The other trend that you need to be able to discuss is the thermal stability of the group 2 carbonates. Now, this is an experiment that you should do in class with your teacher, and a diagram of the experimental setup is shown on the slide. So we have a sample of metal carbonate in a test tube which is clamped horizontally and heated by a Bunsen burner, and we have a delivery tube attached to this test tube, and the other end of the delivery tube is placed in a test tube containing lime water. Hopefully you know, again from Key Stage 3, that lime water is the test for carbon dioxide gas, which should be given off as the group 2 carbonate thermally decomposes. When you do this experiment in class, you should time how long it takes for the lime water in the test tube to turn cloudy as you heat the metal carbonate. Now, in order for the results of this experiment to be valid, there are some variables which must be kept the same. The first of these variables is that we should have the same number of moles of the group 2 carbonate used in each experiment. This should therefore mean that the number of moles of carbon dioxide produced in the experiment is the same each time. The next variable is that we should have the same volume of lime water in the test tube for each experiment. Different variations in the volume of lime water means that we get variations in the cloudiness of the lime water, which may mean that there will be errors made in judging the endpoint of the experiment. The third variable is that we should have the same intensity of heat each time, and this means that the metal carbonate should always be heated with the roaring flame of the Bunsen burner, and the Bunsen flame should be the same distance from the test tube each time. We also need to know the trend in the thermal stability of the group 2 carbonates. And that trend is that the thermal stability of the carbonates increases as you descend the group. The final set of equations we need to know for the group 2 elements are the equations that show the thermal decomposition of the group 2 carbonates. And the general equation for this thermal decomposition is shown below. So again, we've represented any group 2 carbonate with the symbol MCO3. This is because the charge on the group 2 ion is 2 plus and the charge on the carbonate ion is 2 minus, so we need one of each to balance the charge, so the formula becomes MCO3. Now when the carbonate decomposes, we form the group 2 metal oxide, which has the formula MO, and we also produce carbon dioxide gas. Now coming back to the state symbols of this equation, the carbonate will always be solid at room temperature and pressure, as will the metal oxide. Carbon dioxide, we know, is a gas, so it's given the state symbol G. Here is an example for the decomposition of calcium carbonate. So we can see that we form calcium oxide and carbon dioxide as a result of this experiment. If you like, you can pause the video at this point and practice the equations for the thermal decomposition of the other group 2 carbonates. This table summarises the main properties that you need to know in relation to the group 2 elements. So you may want to use this as a revision resource.